In the first part of this video lecture, we saw a lemma and the theorem about sections of measurable sets and sections of measurable and existence of functions that act nicely on the product space. And what we saw, our first lemma was that these functions are measurable. The function that to each point x assigns the measure nu of its section of that set. So once the set E is fixed, and here's E, you see E is not a rectangle. Once E is fixed, then we can consider this function that to each x assigns the measure on the second space of the section at x of the original set E. So the first lemma said that this function is measurable. And then we saw a theorem that says this function that we just showed in the lemma to be measurable. If we now integrate this function, then what we get is something that we can call the measure of E, where we have to show that this has the properties that we want for it to be a measure, meaning how it responds to what we do to the set E here. So will this function be a measure? Yes, it will be a measure. And then my symmetry, this measure will be the same as this one. And because they both will agree on the rectangles, we'll see that this measure is unique. However, we have not yet seen the proof of the lemma and of the theorem. So in this second part of the video lecture, we are going to prove the lemma. So again, let us recap here what we have to prove. We have to prove that this function here is measurable with respect to the sigma algebra of the first sample space. So of course here we're omitting the obvious sigma algebra on the target space, which is just the Borel set. So it is measurable as a function from omega 1 to R. Or to R plus. Yeah, and well, it only takes non-negative values, and this function will be measurable. This is what the lemma is saying. So this is the function that to each point x associates a number. And now how do we compute that number? Well, we have the set E, which is fixed, and then once we take the point x, we can talk about the section by x. The section by x determines a set here, Ex. We can compute the measure of that set, and this is the output of this function. And to prove this, we're going to use this trick that is becoming more and more frequent. We made a statement about that depended on a set E. So we had a set E that was fixed. And what we're going to do is we're going to consider the whole family of sets E for which the statement of the lemma holds. Okay, so every set E in this product sigma algebra such that this section, the measure of the section, is a measurable function of the variable x. We consider this family, and we want to show that, well, we want to show that every measurable set E is in this family, which means exactly to say that G actually equals the product sigma algebra. And how do we show that G equals a certain sigma algebra? Well, one canonical way is to consider a family E of sets, which is a subset. Show that this family is inside G. Show that E is a pi system. Show that G is a lambda system. And this will imply that G, in fact, contains the sigma algebra generated by E. This is the pi lambda theorem. So if this sigma algebra that we take here is if this family here that we take is nice enough that it can be very small, but not too small. It's very small, but large enough so that the sigma algebra generated by it equal the whole sigma algebra of the space, then we're finished. Okay, so we just need to come up with, so our job is come up with the nice family E that is a pi system whose sigma algebra equals the whole product, all the product sigma algebra, and show that G is a lambda system. Yeah, it's a very tortuous and a painful path, but I hope it's a standard already at this point that we have done so many arguments involving pi systems and the lambda systems. So consider now the family that has this property that this function x that maps to each x the measure of the section by x. So first, this function is well defined. What does it mean well defined? We can compute this measure. And why can we compute this measure? Because by the previous lemma, for every set E in this family, when we take a section, this section is in F2, which means we can compute nu of this section. So let's do some brief recap. We have to provide a class E, show that this class is contained in G. So one thing, that the class is contained in G, meaning it has all the nice property that we want, that this function will be, for the sets in this class, will be measurable. It has to be a pi system, and it has to be such that the sigma algebra generated by this class is the whole sigma algebra. So let us show, let us give E. What is E? We're going to take E to be just the set of rectangles. Okay, so E will be this set here, which we already defined. Let's just write again what it is. It's just a set of rectangles. So these are sets which are given simply by the Cartesian product of a measurable set in the first sample space and another measurable set in the second sample space. So this family, it is a pi system. Yeah, you can check that if you take two sets which are of this form and you take the intersection of them, the intersection is also a set that can be written in this form. So it is a pi system. That part we check. This sigma of E equals F1 product F2. Check. That's the definition of F1 product F2, is the sigma algebra generated by sets like this. And so what do we need to show now? We need to show that this family, there are two things missing. So this is where all the rest of the work for this proof will be. So there are two boxes that we still have to tick. Yeah, first, that E is a subset of G. And second, that G is a lambda system. Now, first box, why is E a subset of G? Well, we take a set of this form, and we want to show that this function that maps x to the measure nu of Ex is measurable. And it suffices to see that, in fact, this function is given by this expression. Okay? It will be 0 when x is not in A, and it will be the measure of B when x is in A. And well, we can easily see that by just looking at this. This is A. This is B. And if we take any point x, if x is outside A and we look at the section is empty, so it will be 0. And if x is in A, then the section will be exactly B, and then when we compute the measure, we get the measure of B, and this indicator will give 1. So this equation is correct, and we're going to use this equation again in the future. So let's highlight this equation and remember it. And this implies that we can, this shows that we can take this box. Yeah? Sets of this family, which are rectangles, they have this property that this function is measurable. So we only have now one box to tick, which is that G is a lambda system. It turns out we cannot show that G is a lambda system just like that. We're going to take one step back here and first suppose that the measure nu is finite. It's a finite measure. So nu of omega 2 is just a number. It's not infinite. Okay. We suppose that first, and later on we're going to do some argument to go from the finite case to the sigma finite case. So suppose this is finite, and on that case we're going to show that this family G is a lambda system. How to show that? Well, for a lambda system we have to check three things. First, that the entire space is in the family that we have, trivially, simply because if the space we're taking is everything, then any value of x we take, then we take all the space there. So the function we get is constant. Yeah, this function nu of ex is constant on x. So yes, it is measurable. So this set is if E is the entire space. So the function is constant. So now let's take a look here at the second property, which is the complement. So we have seen already this identity that this set equals to this set in the proof of the lemma of the previous video lecture. And this, the measure of the complement, we can write this as the measure of the sample space omega 2 minus the measure of the section Ex. And here we are using the fact that nu of omega 2 is finite. Otherwise, we cannot write this in general. We cannot subtract something from an equality that involves infinity. And because of this, we have that this is just a number. This function of x is measurable because we're assuming x is in G. So the complement of E is also in G. And this is the second property that we need for a lambda system. So the whole space is in the family. For every set in the family, the complement is also in the family. And now disjoint countable unions. So we take a sequence of disjoint sets, which are in the family, disjoint, they are in the family. And we consider the union of these sets. We have already seen this identity, that the section of a union is the union of the sections. And because nu is a measure, it is sigma additive, so we can take the sum. The union goes out in form of sum. And because of this, this is a sum of measurable functions. Okay, each of these is a non-negative function of x, which is measurable. So we can add infinitely many non-negative functions of x. These will all be countably many. And the result is, by a monotone convergence, or by taking supremum, is a function. So this as a function of x, this as a function of x is measurable. And that means exactly this union here is in the family. It was very painful, but we have now just shown that this is a lambda system. And we can, this finishes the proof under the assumption that we made here that omega 2 has finite measure. Now let us waive this assumption. Okay, so this concludes the proof just by using the pi lambda theorem. Now let's waive the assumption and assume only that nu is sigma finite. And we have done something similar already when we proved the uniqueness theorem at the beginning of week 2. So if it's sigma finite instead of finite, well, let's take a sequence of disjoint sets in the second sigma algebra, F2, that have finite measure, and such that their union is the whole space, omega 2. This is essentially what it means to be sigma finite. Sigma finite, as we stated, says there exists Bn that increase to omega 2, which have finite measure. And now here we're asking them to be disjoint, but we know the usual trick. If it's increasing, to replace an increasing sequence by a disjoint sequence, just to remove all the previous items. So just take dn to be bn minus 1. Then we get this family. And now for this family, we can define a measure nu k index. So it's a measure indexed by k that assigns to each subset B in the sigma algebra of the second sample space the intersection of B with the set dk. Okay? And now given any set in the product sigma algebra of the two sample spaces, we know that the function that just considers the measure k will be f1 measurable, because this is in the previous case that we have considered using the pi lambda theorem. And now we just need to notice that, well, nu of ex will be nu of, here it should be ex, intersection di, which is nothing but the sum, now using sigma additivity of measures. This will be just the sum, this using sigma additivity of measures, and this is just what is the definition of vi. The definition of vi is this. So because this is a sum of measurable functions, it is also measurable. It can even be an infinite sum, as long as, because these being non-negative, an infinite sum can be seen as a limit of finite sums. Finite sums of measurable function are measurable, and limits of measurable functions are also measurable. So this concludes the long proof of the lemma. We still did not do the theorem just yet.